So in this video now I want to start reviewing for the functions portion of our next exam. We're going to go over like some of the base ideas of functions and look at the floor and ceiling functions and special ideas of functions. So let's take, for example, let's start out here with number 1, and we want to draw the graph of f of x equals, and this will be our floor function. You can see that it's got the floor value there. And what it's asking us to do is to draw a graph. Okay? And one of the things that you want to get about this function, the floor function f, it goes from the reals, in this case, onto the integer z. Okay? So what we're going to have is we're basically going to have what we call a discontinuous function. All right? And I'm going to write in a couple of values here. Okay? So let's say, for example, I've got x and I've got y. And I'll let x be like -1. And if x is -1, then y is going to be -1, the floor of -1 minus 3. Okay? And so that'll end up being -4. Okay, great, good. One of the things that I want to do here, because the floor function, is I want to actually give some, fractional values, because, basically I need to evaluate this for some fractional numbers. So I got -0.5, and so the floor of -0.5 minus 3 is going to equal -3.5, which is also equal to -4, right? Because we're going to take the integer that is less than the value for the immediately less than integer, the integer that is less than the value within the floor function. So in this case, -3.5. We'll do it as 0. So this will be 0 minus 3. So that's going to end up equaling -3. And we can actually think, oh, okay, well, if I look at this, like, let me kind of draw my function here. From -1 out to -1 to 0, what we're getting is that the floor function tells us that the value for the function is -4. Okay? So here we go. Here's from -1, x equals -1 out to 0, we're getting this value right here. And then what we're going to do is we're going to use a little open circle. And that open circle is to detail that we are, in fact, not going to include 3. Or, excuse me, we're not going to include the 0 value for x. Then we'll go up to x, and the next one is, well, basically from 0 to 1, right? If we say, for example, we try out 0.5, we're going to get 0.5 minus 3. That equals -2.5. Okay? But it's a floor function, so this goes down to -3. So now we're getting this function. Okay? So we're basically, it's going to have all those values in between. For x between 0 and 1, we're going to get that the floor function gives us back -3. Okay? And what's going to happen basically at each one of these integers, we're going to get what gets called a step function. Okay? So here's our floor function, or the least integer function, as it's called sometimes. And some things to notice, all right? One, this function is not one-to-one. Right? If you notice, for example, -1, we get -1 comma -4, and we also have -0.5 comma 4. So that tells me actually that this function is not one-to-one. Okay? And although it is onto, because if z happens to be the codomain, okay, then we can actually get any integer utilizing the greatest integer function, right? Because all we're going to do is we're just going to subtract 3 from whatever value I have here. So that's going to end up giving me every single one of my integers. Okay, so there it is. Not one-to-one, right? But it is, in fact, onto. All right, there you go. If our codomain is z, if we had a different codomain, say, for example, if I had f r to r, right, we define it that way, then this would be not onto, because, in fact, we can't get any fractional values using the floor function. Now, let's actually take a look at this idea of onto. And let's say, for example, I've got a function f, z onto z, z cross z onto z. So that is, we're going to take duples in z, and we're going to map them onto z. And we want to know whether or not the functions that we've got here are, in fact, onto. All right? Can I get every integer? That's what I'm asking for. Can I get every integer? Or, if we want to look at the definition, if y equals f of x, then and y belongs to z, then, or in fact, y equals f of x, f of mn, excuse me, because we are looking at f of mn, and y belongs to z, then m and n belong to z cross z. So let's think through this problem. Let's suppose I have y, and it equals 2m minus n, okay? And let's say I want to find out what, say for example, if I can get any y and z. So like y is an integer, okay? Y belongs to z. And so, for example, I get y plus n is going to equal 2m. And then that means that y plus n over 2 is going to equal m. Okay? Now the question is whether or not such a y exists. If I select whatever y that I want, will I be able to find an n such that this will give me back an m? So for example, if y was 1, okay, and m equals 3, okay, what I would need is I would need for n equal to 5. But that's fine. That totally works, right? 1 plus 5 over 2 is going to end up equaling 3. So if I have the right y, okay, I can pick an n and it'll give me back m. Totally works, okay? Are there any values, right, that we could choose that we're not going to be able to get, where we're not going to be able to get any y's? And I don't think it's going to actually work out. I think that actually if we look, say for example, and we make it y, right, minus 2m equals negative n, and this then gives me that n is equal to 2m minus y, right? As long as that's the case, right, as long as n is equal to 2m minus y, we're actually going to be able to get any y that we want, right? So that's actually going to end up, it's going to end up working, okay? It's going to actually end up working really well for us, okay? So any y can be gotten using this function. So that means that this function is in fact on 2. N equal to m squared minus n squared is in fact on 2. So one of the things I want to do with something like this is I'm going to say, okay, well, f of mn is going to equal m minus n times m plus n. And this is going to actually help me think through this process. So let's say, for example, let's take a y equal to m minus n times m plus n. And let's say, for example, that y equals 10. So we want to see, is there a value for m and n that's a difference of, in this case, squares? So m, if we have a set of values, okay, for m and n, we could have 5 times 2. We could have 2 times 5. Okay, we could have 1 times 10, and we could have 10 times 1. Those are options that we could have. Now, if I take this, then we're going to get some system of equations. We'll get m minus n is equal to 5. We get m plus n is equal to 2, for example. And let's see whether or not we can actually find a value of m that will give us that. So now we get m, right, when we add the two together, we get m equals 7, or 2m equals 7, and that means that m has to equal 7 over 2, and that doesn't work because m belongs to the integers. So that's not one of them. What about this? We take m minus n equals 10, and we get m plus n equals 1. Okay? So now what that gives me then is 2m equals 11, and then m must equal 11 over 2. Well, again, m belongs to z, so m cannot be 11 over 2 either. Now there's no other factors that we have for 10, so consequently what that means for me is that means that there's no way to get 10 from m squared minus n squared. It's impossible. So consequently, f of mn is not on 2. There is, my counterexample, there is an integer that gives us, there is an integer, all right, in z, or an element of z, that we cannot get to using two integers, m squared minus n squared. Let's now determine if z to z is 1 to 1. So let's say, for example, I have f of n equals n minus 1, okay? And if you'll notice here, we can actually, let's use a graph in order to see that this is in fact 1 to 1. Okay. All right. And notice that it's z to z. So all we're getting is we're going to plug in, right, 1. So when we plug in 1, we get 0 back. And then we plug in 2, we get 1 back. 3, we're going to get 2 back, so on and so forth. Now, the lines are not connected here. They're not connected because this is from z to z. Okay, so we're going from the integers to the integers. But you'll notice, right, this passes the horizontal line test. We don't have any redundant outputs. Okay, we don't have any outputs that repeat. So this one, in fact, passes the horizontal line test. So it is 1 to 1. On the other hand, we see something like this. F of n equals the floor of n over 2. Well, all we have to do is we have to find two n's such that f of n equals n divided by 2, right, equals x1, and it equals x2. Okay? Right? So, like, basically that it equals, or for x1, f of, that's what I mean is actually, f of x1 equals x1 over 2, okay, equals an f of, which equals x2 over 2, which equals x2. And x1 does not equal x2. So this is a ceiling function. So what I'm going to do is I'm going to choose two numbers. All right. I'm going to choose, let's say, for example, I choose 1 and 2. Okay. So f of 1 is going to equal 1 over 2, which is equal to 1. The ceiling of 1 over 2, which equals 1. Then we take f of 2, and that equals the ceiling of 2 over 2, and so that ends up equaling 1. Right? So f of 1 equals f of 2, and this means f is not 1 to 1. So 1 to 1ness, basically what we need to do, either we need to show via, say, something like a horizontal line test, or we need to kind of think through. There are some proofs that I put up in terms of videos that you can use. Or we can use this counterexample. And a counterexample is just you find two values that we input into f, and what they give us is the same output value. All right. Now, let's say, for example, I want to determine if each of the functions is a bijection from R to R, and if it is not, state which requirement is not met and how you know. Well, let's take, for example, f of x equals x squared plus 1. To be a bijection, that means that f is 1 to 1 and on 2. That's what f is. So f is both of those. Well, we already know f of x is quadratic, right? It's x squared plus 1. And so, for example, negative 3 squared plus 1 is going to equal 10, and 3 squared plus 1 is also going to equal 10. So, f is not 1 to 1. But here's the other thing. F is also not onto. Notice that we're going from R to R. Our codomain is R. So f is not onto because there does not exist a real number R or a real number in R, excuse me, in R such that x squared plus 1 is equal to 0. We can't get back out 0. 0 is a real number. Okay, so consequently, this is kind of impossible. We end up with x squared equals negative 1, right? Okay, and that's not possible in the reals. So consequently, f is also not onto. Okay? Let's consider f of x equals x cubed. And if we kind of think about what the x cubed function looks like, 1, there's no restrictions on its domain. Okay? And in fact, we're going to be able to get all the negative values and all the positive values. Furthermore, this one, it doesn't have any bumps in it, any issues with it at all, right? So it passes the horizontal line test. If we think about it as a curve in the Euclidean plane, all right? And x cubed equals y for y belonging to all the reals. So we actually can find all the reals. So f of x equals x cubed is 1 to 1 and onto, meaning that it is both an injection and a surjection. Okay? So f is a bijection. What about f of x equals x squared plus 1 over x squared plus 2? Okay, well, now this one has a problem. This one is not onto, as 0 equal to x squared plus 1 over x squared plus 2 is not possible. We get really actually quite close to 0, but we can't actually get 0. Well, actually, no, we can't even really get close to 0. We get close to 1. Okay, but 0 is not possible. So f is not onto. And in addition to that, it's also going to be not 1 to 1. So for example, if I take negative 3, so let x equal negative 3, I get, this is negative 3 squared plus 1 over negative 3 squared plus 2, which ends up equaling, and this is, by the way, in parentheses, which is going to end up equaling 10 over 11. And that's equal to 3 squared plus 1 over 3 squared plus 2. Excuse me, plus 2. So, f is not 1 to 1. Okay? So you want to be able to actually also be able to detail whether or not a function is 1 to 1, is it onto, does it have an inverse? Remember also that for a function to be 1 to 1 and onto, to be a bijection, it has to be 1 to 1 and onto. To have an inverse, it has to be a bijection. Okay, so those are the requirements that we have in order for a function to actually have those characteristics and qualities, right? Those are important properties. Also, don't forget to go through and do the homework on functions and the homework on logarithms. I've opened up the solutions to that, so you can go take a look at that as well. Okay, that's the end of the lesson.